All right, so our next presenter is Stephen Okacha, who is a PhD student in the Department of Mechanical Engineering at the University of Alberta. He works under the guidance of Dr. Ben Jar, and his research focuses on structural integrity and the fracture toughness of rail steels. His work includes developing non-destructive methods for determining the fracture toughness of rail steels. Join me in welcoming Stephen.
Good morning, everyone. Just to clarify, can you hear me and can you see my screen?
It looks good on my end.
Thank you very much. So I'm representing my research team, and today we'll be presenting the topic, the relationship between the fracture toughness and the average grain size of high-strength rail steels. I'll just jump in straight into my presentation. Okay, so we actually know that the microstructure plays a very significant role when it comes to the mechanical and the fracture properties of metals. And when we talk about steels, that is of no exception, because we can see steels being applied into several functions, like you can see here, like rail steels, pipelines, and even engines. And this actually gives a concern for engineers to try to understand at which extent it could fail. And so this leads us to try to understand the terminology, which is the fracture toughness. Just to give you a very simple definition of what the fracture toughness is, it is the energy that is required to initiate or to propagate a crack that is existing in a structure. We in the rail industry, we can just say it is the load carrying capacity that the rail can handle before it fractures. So previous research from the Cow Research Lab, we've been able to look at the severity of different derailments that are occurred over the past years. And we identified that the rail itself, the rail component and its components are the major contributors when it comes to derailment. And from the second figure that we have on the right, even if we can see a significant drop in the derailment per year, it's still very high and still a major concern. And this is the reason why we want to go deep into the rail steels and study it microstructurally to see what is really going on. So if you look at the two images we have in front of us, these are the microstructures of the rail. This is at 50 microns and at 400 nanometer scale. We found that from literature that first of all, the first thing is that the fracture toughness on normal conditions are inversely proportional to the strength of the rail steels. And then the works of Yamada, Carlson, and Ricci, we're able to understand that it is the grain size, and when we say the grain size, the para-austenite grain size that are responsible and have a higher sensitivity when it is related to the fracture toughness. And then when we talk about the interlaminar spacing, like the image you said, right, that only affects the strength and has nothing to do with the fracture toughness. So it gave us a clear direction of where we had to be going to. And then the problem now is that even if we have to get the fracture toughness by using the ASTM standard, based on two different specimens we have, like the SCMB and the CT specimen, the problem is that we don't have a microstructural parameter that is included in the models that has been given us, that is being given to us by the standard. And then apart from that, majorly, if we have to still work with ESTM approach, it's very expensive to do, it's time consuming, it's labor intensive. Like if you look at the diagrams, you can see some little cracks at the edge. Performing that using pre-fatigue cracking is very expensive and time consuming. And even if we have an installed structure, we cannot still cut out from it to start performing this kind of experiment. And these are the problems that directed us to go towards this area. So the question now is, what is the relationship between the fracture toughness and the microstructure of high-strength rail steels? For our scope, we looked at 9 rail steels. 3 of them are from CN, and the remaining 6 are from TTCI. Here we can see the microstructures, the type of microstructures that the rail steels have, and then we took from locations majorly from the head and just very few from the feet, since the area of interest is from the head of the rail. And like we've said, the focus is just on the fracture toughness. Our objective is to find the correlation between the grain size and the fracture toughness. Secondly, to establish and to validate a fracture toughness model that will include a microstructural parameter. And then also see and investigate whether or not the heat treatment plays any role to the effect of the fracture toughness. And finally, to suggest potential technologies for fracture toughness estimation other than the ASTM approach. So what we did was to take some samples from the head and the foot, as I said earlier. We cut it, we polished, etched it using 2% nitrile, and took it to the optical microscope for imaging. We had about 135 fields of images. And then by using a visual inspection method, we started looking at the structures of the real steels, and we're able to even if it's difficult, but we're able to see grain sizes, across the real steels. And then by using the ASTM E112 guidelines, we're able to map out and get what we call the mean intercept length. The aim of doing this is to see if we can estimate the average diameter of the real steels. So looking at the slides here, the first table we have the mean intercept length, we have the ASTM number. All these are microstructural parameters, but the main interest is the average grain diameters. The average grain diameters are ranging from about 42.9 to about 71.1 microns. And then from the table from the right, these are the mechanical properties of the 9 real steels. These were performed by a previous student, Yu et al. From 2017-2018, where we got the mechanical properties and the fracture toughness of the real steels. Of course, our interest is the fracture toughness and also all these other parameters too. And then what we did was to see if we can correlate this to the grain sizes and the fracture toughness. So when we did that, we found a fairly relative proportional relationship between the fracture toughness and the square root of the grain diameters. Now, the issue is, for instance, if we look at EV, despite the fact that EV has the highest grain sizes, it does not necessarily mean that we have the highest fracture toughness. And this actually means that there are other factors that plays a vital role, apart from the microstructural average diameter, in estimating the fracture toughness. And so with this result, we have to go back to the basics to find out what's going on. This is going to be a little bit more academic but just to explain, when we have a real steel from normal, standard, and ambient temperature, we know that the mechanism for failure is going to be ductile, and it follows a sequence of void nucleation, growth, and coalescence. And everything is just based on an energy included into the whole mechanism, just like what the previous presenter suggested and told us about the energy that causes fracture. But one thing that we need to note is that fracture actually occurs macroscopically and microscopically. And then when we go to the field and we see the fracture, yes, that is macroscopically. But microscopically, we also have things going on. So let's look at it one after the other. So if we take a single edge notch bending sample and perform quasi-static loading on it, we have a parameter which we call the crack tip opening displacement. The crack tip opening displacement is equivalent to the ratio of the energy and the yield strength. And then when that crack tip opening displacement becomes critical, we know that fracture has occurred, and that relates to the fracture toughness. But when we look at materials that obey the small scale yielding criteria, then we can also get another model which says that the critical energy to cause fracture is also equivalent to the square of the fracture toughness and the modulus. And so when we combine those two equations, we can have a simple model based on macroscopically identified components, as the fracture toughness is equal to the square root of the modulus in plane strain, the yield stress, and the critical crack tip opening displacement. But now let's look at it and what happens microscopically, owing to the fact that we already know what we've gotten from macroscopic events. Macroscopically, when we look at the microstructure of the real steel, we can find that in several parts of it, we can find inclusions. These inclusions are non-metallic oxides that are added as part of the constituents for the microstructure. It is believed from research, we already know that it's at this point of inclusion, in most times, that we have the same process of void nucleation, growth, and coalescence, meaning that the voids initiate at that point, it grows, and then it combines together. And so when we look at the point of strain, when we look at it from a strain point of view, the equivalent plastic fracture strain at fracture is also equals to the ratio of a critical CTOD and a distance. That distance, we call it the characteristic distance. That distance is just a microstructural distance, which is the distance between the joining of all the voids. You can also see it here from above. It's when all the voids join, we have that length. And so when we combine the model we have from the bottom and the microscopic model, we can find a more complete model, which we call the critical fracture strain model, which is what we have below here, which is having the mechanical properties, the microstructural parameter, and the strain value, the fracture strain value. So with this, we've gotten theoretically, we went back and we decided to use mechanical testing to estimate modulus and yield strength. And then we searched the literature and we found some very interesting values that the CM is taken as 3 for steels. Haggard did that. And then for our characteristics distance, we equated it to 6 times the grain diameters that we had. This was suggested by Ritchie. And then for the equivalent plastic fracture strain, we got that from the tensile test, the tensile fracture strain, and used the Bonora's model to get that for the equivalent plastic fracture strain. So what we tried to do was to compare our predicted fracture toughness and that of ASTM. And this is what we got. We saw a couple of our values matching with that of ASTM, although some were kind of like outliers, like the CZ and the CV, EV. But this actually calls for more research why this is happening. So something we also noticed is that for CZ, after the production, there was no heat treatment that was done. And so it had the lowest fracture toughness. For the hyper-ectectoid rail steels, which have more carbon contact, they were the next highest. And for all those that were done deep hardened, head hardened microstructure, they had the highest fracture toughness, which is something we expect. So we know that at least with different microstructure, even if we can't get the exact values, we can group it to some extent. And so now that we have this model, we decided to look at normal conditions. What happens in normal conditions? Of course, we're expecting to have a standard fracture toughness. But when we have cold temperatures, very cold temperatures, we're expecting, just like what some of the previous presenters have explained, we're supposed to have a slight increase in the modulus and an increase in the yield strength. But overall, a drop in the fracture toughness. The reason why we're doing this is that if we have a theoretical value for the fracture toughness and we take it to the field, if we take our values from the field and we find something below the theoretical values we have, then we know that it's a sign that something is wrong. So it calls for inspection, it calls for maintenance, and things we can do. If the structures or the rail steels are having internal damage, definitely we'll still have lower fracture toughness. And then for materials that obeys the small scale yielding criteria, like the rail steels or structural alloys for bridges, they generally have very low fracture toughness in the range of like 30 to 45. And then for materials that don't obey, like pipelines and pressure vessels, nuclear vessels, we're supposed to have very high fracture toughness because of these two parameters, in the range of like 100 or 150. So just to conclude all this we've done, something we found out is that because of the sharp notch tip, which produces very high pressure, or some can call it high stress triaxialities, they actually reduce the characteristics distance and also the fracture strain. And then that same high pressure is responsible for reducing the overall energy that is required for fracture. And so that's why in cold periods of very sharp notches or materials like that, we have lower energies to cause fracture. The CM, which we use from Haggard, which we use as 3, we later found that it's not a constant. And this is something we're actually working on right now. We know it depends on the microstructural length, and we're trying to develop models to perfect this. And then the 6 we also used is just a fitting parameter for this research. We believe that the works of Clinton, Rice, and Tracy will help us evaluate this into a more perfect model because they work with void growth models. And most importantly, the 5th point is that we can use different technologies right now in estimating the fracture toughness. Technologies like the tensile test, the simple punch, indentation test, they can help us in estimating the fracture toughness. And so when we have real stocks, we can just test them quickly and know what's going on. And possibly in the future, with better technologies, we can use it for real-time mechanical inspection. I want to thank the sponsors for this research, Transport Canada, CN, NSERC, NRC, and TTCI for giving us a headway into this research. Special thanks to Calvin Hodder, Andrea McDonald, and the technicians from Microstructure for making this a reality. These are some of the references I used for this work, and thank you very much.
Hi, Stephen. What a great presentation. There was a lot of interesting information in there. So we do have a question from the chat. Comes from Daniel Zablewski from MRC. Have you looked at the presence of either ferrite or cementite at the grain boundaries and how that affects your KIC values?
Okay, thank you very much. Yes, we actually saw some of the rail steels like rail 3 and rail 4. They had some cementites on the grain boundaries. But just like what we said, like I said earlier, the grain boundaries do not really play that role. It is the voids. Because we found some of the rail steels had voids in it. That was where, the problem came and what actually controlled the fracture toughness. So right now, there are little or no effect from the cementites from the grain boundaries at this stage right now. I hope that answers your question. Thank you.
Yeah, that's great. There's one more from Suju. Interesting presentation. Your K values were not related to laminar space, but it was related to the strength, and K decreased with strength. Can you please comment on any observations of laminar space and K for steels?
Okay, thank you very much. So you see the laminar spacing, like what I said, the laminar spacing just affects the strength. So, but that's where the importance of heat treatment comes in. No matter what we do by changing the laminar spacing, it doesn't really do anything on K. K remains what K is, and is only affected by the para-austenite grain sizes. So even if the laminar spacing changes inside just one para-austenite grain size, it doesn't affect the K still. What matters is because in reality, or let's say theoretically, what really happens is that two voids, the distance between two voids is taken as one para-austenite grain size. So the larger the voids are, the larger the grain sizes are, the more it affects the fracture toughness. But inside the grain size, no matter how the laminar spacing changes, it doesn't really affect the fracture toughness, at least for steels. For materials like aluminum, we're not sure about that for now. I hope that answers your question too.
Perfect. Thank you so much, Stephen.